Hi there, we're going to work through some questions in 2.6, the pre-lecture assignment, and some of them are somewhat self-explanatory. I'll try to move through them quickly. Determine the intervals of the domain over which the function is continuous. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. All right, so we're looking for continuity. Now, continuity, or a function has continuity, or a function is continuous for values of x wherever you can run your pencil along the curve and not have to pick it up, or where you don't run into some sort of wall where you can't go any further, like an asymptote, which we have not seen asymptotes yet. We will get to that later in the course. Right now, we're mainly looking for holes that we might have to jump over. And there are no holes here. And you can see that the y values keep going up towards infinity, down towards infinity, and the x values keep going left towards infinity, right towards infinity. There is no stopping this thing in either direction, either horizontally or vertically. But I'm interested in discussing values of x for which the curve is smooth or continuous. So it is continuous for all values of x. So it is continuous on its entire domain. All right. Determine the intervals of the domain over which the function is continuous. Again, we're looking at values of the domain, so starting at x equals 4 right here and moving towards x equals infinity, or x towards infinity. X can't actually equal infinity, but moving towards it, we could have continuity from that point, from including 4 and all the way towards positive infinity for x values. Okay, so continuity, again, determine the intervals of the domain over which the function shown to the right is continuous, and you can see a little tiny hole there. Try to zoom in a little bit. It's not really zoomable. So I can see that that little hole is happening where x is -3, and everywhere else this thing looks continuous. I don't see any other holes, and this thing does stretch out towards positive infinity for x values and negative infinity for x values. So I will say, what was it, -3? Let me just double check. Yeah, it's at -3 is the hole. So I will say that this thing is continuous on the interval from -infinity to -3, not including -3 though, and then from -3 again towards positive infinity. Okay, so notice I put the little union symbol right there where there was a gap. For the piecewise linear function, find f of -3, -1, 0, 3, and 5. Okay, so this is called a piecewise function, a piecewise defined function, meaning that the function is defined into pieces. The first piece is whenever x is less than 1, and the second piece is for whenever x is greater than -1. So if I graph this thing in GeoGebra, I'll show you what f of x, the first function, was. Let me just show that again. Find it. F of x equals 3x, so that would be y equals 3x. Okay, and this piece is only good though for values where x is less than or equal to 1. So looking at my GeoGebra graph again, where x is less than or equal to -1, here's -1 on the x-axis, and starting there, which is actually right here, is the first point, and then anywhere to the left of that for values of x that are less than or equal to -1, that would be the piece that I want right there. And so if I was graphing it, I would only want to show those. I would show a dot starting here and then the rest of the line moving from here. I would not show any of the line above A. But this is actually a question that's asking us to just use the equation. So let me show you that again. So the equation 3 times x for all x values less than or equal to 1, negative 3 is less than or equal to negative 1. Get rid of that. So I'm going to move this a little bit so we can see better. So here at x equals negative 3, if I follow if I follow the graph down here, there is a point on the line 3 times x. When you plug in negative 3, well, 3 times negative 3 is negative 9. So you can see how the point lands right there. So the value of y when x is negative 3, or the function's value when the input is negative 3, is negative 9. And I could have figured that out just by doing the simple math of saying, let's see, try some, f of x is equal to 3 times x when x is less than or equal to negative 1. So f of negative 3 is equal to 3 times negative 3, which is equal to negative 9. Okay, so that is the reason that this answer just has to be right, negative 9. F of negative 1. All right, so even when it's just equal to negative 1, we still use 3 times x. So 3 times negative 1 will be negative 3. And if I show you on GeoGebra, when I do negative 1 and 3, or negative 3 rather, it lands right there on my line. Okay. So f of 0, though, well, 0 is not less than or equal to 1, so I'm going to have to use the other piece where x can be greater than negative 1. 0 is greater than negative 1. On my GeoGebra, notice that here at 0, I would have, if I was using the same piece definition, I would use this point right here as my solution. However, we're going to have to use this other piece, which is x minus 2. So that is a line that goes through negative 2 on the y-axis and has a slope of positive 1, y equals mx plus b. So I'm going to go back to GeoGebra and show you that when I go to, what was it, negative 2? Yeah, negative 2 with a slope of positive 1. So if I go to negative 2 and then do a slope of positive 1, up 1 and over 1, this is the line I have. So for x values that are greater than negative 1, so from this line over to the right, I want to be using that second piece here. So where you see G and H, that line is my second piece, and it starts right at x equals, right after x equals negative 1. So I'm going to take a little picture of this and bring it over to my notebook. And I want to show by highlighting that this first piece here, is from x equals 1 over. And it keeps going. My second piece starts there and goes that. Oh, I think I had that backwards. Let me do that over. I meant to highlight this section right here. And then the second piece is going from here over, like that, on the other line. So you can see it's not a straight line. It has a little turn to it. And so that's the second part we want to do. Okay, so now we'll do f of x is equal to x minus 2 for x strictly greater than negative 1. That's what we have there. So for instance, f of 0 will be equal to 0 minus 2, which is minus 2. Right, so you can see, I take my little, let's do a pen this time. If I go to 0 for x, then I would be right here at negative 2 on the blue portion, the blue piece. And for negative 3, just to complete that, for x equals negative 3, remember I was right there at e. Okay, so to answer the question, I want to go to negative 2. 3 is also greater than negative 1, so I will use that second piece again. So plugging in 3 minus 2 is going to be, 3 minus 2 is going to be positive 1. And again, 5 is greater than negative 1, so I will still use that second piece. 5 minus 2 is 3. All right, so that's that one. Let's go on to another one. All right, this one we're going to graph, but they give us choices here. So it says that we want to have y is going to be negative 2 whenever x is less than or equal to 0. So notice that all of these pictures start on the y-axis. I have little dots on the y-axis. So we just have to pick which one has the right pieces. So when x is less than or equal to 0, we want to be at negative 2, which is lower than negative 1. So I know that my negative 2 has to be lower and moving to the left of 0. So this one looks kind of good, but there's a hole. And this says for x less than or equal to 0. So this bottom piece should have a closed circle, and the top piece for negative 1 should have an open circle. So that's not the best choice. We're going to look for another one. Here we go. Nope, not that one. This one. This one has to be it. Graph the piecewise defined function. Okay, again, now this one's a little tougher. There's a lot to choose from here. It looks like all of the dots are where they're supposed to be on x equals positive 1, so I'm not so concerned about where the dots, the beginning of each piece is. They're all in position in the right place. So now I'm just concerned with which pieces are correct. So when x is greater than 1 on the right side, notice that there is a positive slope for values of x that are greater than 1. So the positive slope piece would be uphill. So the piece more to the right should be uphill. And this is the only one that has that, so I'm betting on this one. And let me just double check the other piece. The other piece for when x is less than 1 or equal to 1, so it'll have a closed circle, or a closed circle, will have a negative slope. You can see mx plus b, mx, m is negative 1 here. So it'll have a negative slope, meaning it's downhill whenever you're to the left of positive 1. So the left-hand piece should have a closed circle, and it should be going downhill from left to right. So you can see if I start on the left and start moving along that piece, it's going downhill. So that does look really good. Yes. Okay. Give a rule of the piecewise defined function. Give the domain and range. Okay, so let's look at this thing. Okay, so the pieces are both on x equals 0 axis, and when x is equal to 0 or smaller, y is going to be negative 2. when x is equal to 0 but not equal to 0, strictly greater than 0 and larger, it's going to be a y value of 3. So which one of these says that? Or we make it ourselves. Oh, okay. So what's the difference here? Okay, so one of them gives us the option for less than or equal. Yeah, that's what we want, because this one is less, this one's equal and less. So it's going to have to be A. It wouldn't be this one, because that says greater than or equal, and we have an open circle on the greater part. And then if x is less than or equal to 0 is the place where the dots are for both of those. When it's less than or equal to 0, y is -2. And when x is greater than 0, y is equal to +3. Right? Give a rule of the piecewise defined function, give the domain and range. Oh, that's the one I just did. There's the second part. The domain. Okay, so the domain, well, the domain is all values of x, because from 0, including 0, all the way to the -infinity, there are x values on the curve. And also after x equals 0, it continues to the right on that second piece. So the domain is continuous. Why? Oh, so I don't want to do a list. Those little curly braces mean I would list out a few values, like a few individual values, like if I had just like only a few locations on the x-axis that could have points. But the domain is continuous, so I want to do an interval, and it is -infinity to infinity. And there we go. I'll go ahead and check that. Yes. And what is the range? The range are the y values. The y values cannot be either -2 or +3. So this time I do want to do the listing version with the curly braces, not an interval, because it's not a continuous range. It's a discrete range with only a finite number of values. So -2 and +3 are the only y values in the range. So that's it. So that's your pre-lecture for 2.6. Hope that helped. I'm sure it did, because why wouldn't it? If you have questions, please do let me know, and I will see you in class. Thanks.